Continuing our Hess's law journey here. For the oxidation of ammonia as shown in the unbalanced reaction above, use the following information. So this again is take some combination of these three reactions and use it to make this reaction. But, new thing, they warn us this reaction is unbalanced. So we can't even start work on this until we have a balanced version. Let's take care of that right away. I'm just going to write this again so I have room to put coefficients on it. NH3 plus O2 arrow NO2 plus H2O. Okay. Nitrogen is 1 to 1. That looks good. Hydrogen 3 to 2. Not so good. We can take both of those to 6. That's 6 hydrogen. And that's 6 hydrogen. But now, having done that, I also have 2 nitrogens. So we'll need a 2 here. And what does that do to our oxygen? We have 4 oxygen here, plus 3 more is a total of 7 oxygen. So you could put 3.5 in that spot. And on my previous attempt recording this one, I actually used this reaction and did the whole problem. And only when I got to the end did I notice that they say balanced using lowest whole number coefficients, which means that 3.5 is no good. If we're going to do this, we need to double all of these coefficients to get rid of the 0.5. So doubling these, we're going to get 4, 7, 4, 6. That'll be our balanced whole number reaction. That's what we have to work with. So don't be like me, balance your reaction and then double it. Okay, now that we have all that, we can actually dig into the Hess's law stuff. We need a reaction that has 4 ammonia on the left. Reaction 1 is the only one that contains ammonia. It is on the left, great, but there's only one of it and we need 4. So I'm going to put 4 times reaction 1. That gives us 4NH3 arrow. 4 times a half is 2 nitrogen. And 4 times 3 over 2 is 12 over 2, which is 6 hydrogen. Good, so there's our ammonia sorted. 7 oxygens. Oxygen comes from 2 different places, as it often does, so skip that one. It's too hard to know how to combine these two, so we'll just hope that that takes care of itself as we work on other substances. We need 4 NO2 on the right. Reaction 2 is the only one that has NO2 in it, so we have to use this one. It is on the right, that's good, but again, we need 4 of it, so 4 times reaction 2. That'll be 4 times a half is 2 nitrogen. 4 times O2 is 4 O2s. And 4 times NO2, of course. And finally, we need a reaction with 6 H2O on the right. This reaction already has H2O, and it's on the right, but we need 6 of it. So to make this happen, we need 6 times reaction 3. That'll give us 6 hydrogen. 6 times a half is 3 oxygen, arrow, and 6 H2O. We're out of reactions, so hopefully that's all the stuff we need. If we add this up and cancel spectators, we have 2 nitrogen before and after. We can lose those. We have 6 hydrogen before and after. We can lose those. So we end up with 4NH3. 4 oxygens plus 3 oxygens is 7 oxygens. And then we get 4NO2 and 6 H2O. 4746, that's good. That's the reaction we wanted. And the big finish, we get to calculate a delta H now. We did 4 times reaction 1, so we get 4 times this delta H. I could maybe do that in my head, but let's try it not to mess it up. 4 times 46.1 is 184.4. We did 4 times reaction 2, so we do 33.9 times 4. 130, sorry, 135.6. And we did 6 times reaction 3, so negative 242 times 6, calculators are hard, is minus 1,452. None of these were flipped, so all the signs stay the way they were originally. And when you add up these 3 reactions, you add their delta H's. So we get 184.4 plus 135.6 plus negative 1452. And I swear I hit the negative there, but it didn't take. Minus 1452. And from that I got minus 1,132 kilojoules. Or, because that's over 1,000, you could say it 1.132 megajoules if you like changing units. Those are both valid answers. And whoever did the key agrees with me. That's a nice feeling.